Hey guys, welcome to section 1.1 called Parent Functions and Transformations. Today we're just going to start and just dip our toes into transforming parent functions. We're first going to figure out what parent functions are. So our first learning target is I can identify basic parent functions. Here in this paragraph before our table, it says functions that belong to the same family share key characteristics. The parent function is the most basic function in the family. Functions in the same family are transformations of their parent function. So basically, a parent function is where every function graph starts. So our parent function is the most basic, and then every function in that family of the parent function are just transformations of their parent function. So in order to get to the transformations, we have to first be familiar with some parent functions. Now, these are just a few. We're going to learn a lot of different ones the rest of the year. Okay, first let's look at the four families we have here. We have a constant, linear, absolute value, and quadratic. Hopefully these all are very familiar to you or look familiar, and now we're going to get a little deeper into them. We're first going to start with the constant, which is just a horizontal line. We really don't do much with this one, but it's good to know what that is called. Remember, it's constant because it stays at the same y value the whole time. So your parent one is f of x equals 1, where we would say that this line is a y-intercept of 1 and it's just making a horizontal line. Okay, another familiar function is a linear function. We are used to linear functions being written in slope-intercept form, most likely. Now, this function f of x equals x is actually in slope-intercept form. However, the slope is just 1, because remember, any x is 1x. And then the y-intercept is actually 0. So here's our y-intercept, and our slope would be up 1 over 1, up 1 over 1. Okay, so every linear function starts from this one with a slope of 1 and a y-intercept of 0. All right, then we have absolute value function. Now remember, absolute value is the distance a number is away from 0, and it's always positive, hence why our graph lies above the y-axis. All of the output values are positive. And that is why our range down here, remember range represents y values. That's why y values are greater than or equal to 0, because every absolute value of a number is 0 or greater. Finally, we have our quadratic family, whose parent graph is f of x equals x squared. And maybe you remember this is called a parabola. Our quadratic function is also known as the squaring function, and what we do is we just square the input values. And if you remember, anytime we square a number, which is multiplying it by itself, we will always get a positive number. Hence why the range on this one is also y is greater than or equal to 0, because we are never going to have a negative output. One other key thing on both these graphs is the point 0, 0. On the parent function is known as the vertex. This is important to know when we start moving them around and transforming them. All right, let's move on. Example 1, identify the family to which the function belongs. Compare the graph of the given function to the graph of its parent function. So basically the goal here is we look at this graph in A. Obviously we see the graph, it's V-shaped, and then we also see the function f of x equals 2 times the absolute value of x plus 1. So that kind of gives away the family. We see it in the function, and we should also be able to identify that it's V-shaped like our parent graph up there. So the family here is absolute value. And then it says compare it to its parent graph. Well, first of all, we know the parent graph is f of x equals the absolute value of x. So I'm just going to find some points on that graph and plot them so I can see what it looks like compared to this new function that's plotted. I'm just going to put the input x values of -2 to +2. You could put any x values you want in there. So if we're plugging these x values into f of x equals the absolute value of x, means we're taking the absolute value of each of these inputs. Remember, we will always get a positive number. The absolute value of -2 is 2. The absolute value of -1 is 1. The absolute value of 0 is 0. Absolute value of 1 is 1. And the absolute value of 2 is 2. So these points are ordered pairs now. This first one is -2, +2. -1, 1, 0, 0, 1, 1, 2, 2. Obviously, I could keep going on forever in either direction. For instance, if I plugged in 3, we know the absolute value of 3 is 3. Just like -3 has an absolute value of 3. So we see that we have this V-shaped graph, which is going up 1 over 1 in each direction. Okay. The first thing I noticed that's different on the new graph than on the parent graph is that the vertex is at the point 0, 1. So it looks like our new transform graph has moved up 1 unit. Another thing I noticed is that the blue V is a little skinnier than my parent graph. So something has happened that it got skinnier. So I'm just going to say, I'll say it's thinner. You could put skinnier too. Whatever you prefer. And I wonder how this happened. One thing I do see is that I see a +1 here at the end in the function. I'm wondering if that has to do with the moving up 1 unit. And then I see this 2 out in front of the absolute value of x, and I'm wondering if that has to do with my function looking thinner, or heck, maybe it got taller. We'll see. Moving on to example B, I have a U-shaped graph, which is a parabola. We know a parabola is in the quadratic family. So just like I did the last one, I'm going to make a table and plot some of the points from our parent graph, which is f of x equals x squared. I'm just going to put in the same x values I did with my absolute value one in part A. When I have f of x equals x squared, what I'm doing with my input values is squaring them. And remember, we should always get a positive number when we square, except for obviously with 0, we get 0. And filling in the table, I end up with 4, 1, 0, 1, 4. So my first point is -2, +4, -1, +1, 0, 0, 1, 1, 2, 4. And again, I could keep on going. I could have 3 and I square it, get 9. So I have the point 3, 9. That'd be off my graph, so it's not really going to do me much good to look at right now. So I'm going to sketch this parabola, my parent graph, and compare it to my transformed graph. The first thing I notice is that my transform graph's vertex has moved to 3, 0. So it appears that we have shifted or moved right 3. Okay, this also appears to be much wider. And that's thinking horizontally. You could also think like maybe it got smushed down or something. So that's something different. Okay, so now we can see how graphs can kind of change. Now we're going to get a little more formal with them in the next video.